Hello everyone. So in this lecture we will discuss some topics about mechanical properties of materials and starting with the property of superplasticity. Now when you talk about superplasticity, you know what is a plasticity. We know what is a plasticity is. Plasticity is sort of when due to some sort of stress applied to a material, there is a movement of dislocations. And if you go by the stress and the strain plot, so if you are applying, say you have a dog bone shaped sample and tensile stress is being applied, so in this region there is necking if you are using a metal, and it ultimately leads to fracture. So this process of necking starts when in the stress versus strain plot there is a deviation from linearity, and this is known by the yield stress or the point of stress where the plasticity starts. Now, this is the basic plasticity concept. Uh, Now, what is actually a superplasticity? Now, superplasticity is the ability to material to withstand very large deformations without being getting without necking. So let's put it in this way. So it can the material or a superplastic material is that material which can withstand very large deformations, very large deformation, and there is intention, and at wrestling there is no necking taking place there. The necking is as just shown by in the previous few minutes, when you have a sample like this and you are supposed, and this is getting a tensile stress being applied here. I'm not sure. So this region, the cross section area starts to get reduced. Okay. Though now this cross section area, if you take into consideration, you get in the stress strain curve, you get two stress and two strain, whereas the amount of stress or strain in the plot, that is the engineering stress, engineering strain, we are not going to that. So what happens in a superplastic material is that this phenomena of necking is not taking place. This doesn't take place, and so we have a very large elongation. So and the elongation in excess of 100%, one even 1000% takes place. So that means this region, this gauge region, it elongates, it starts to elongate without any reduction in the cross-sectional area. So no reduction in cross-sectional area is taking place. So practically, in other words, you can see that in this case the engineering strain or the engineering stress, they are equal to the true stress or to strain. You can put it in that way. Okay. Now, this property of superplasticity is related is related to existence of very high high strain rate sensitivity. And it usually occurs at temperatures which are more than the half of the melting temperature. So it shows a large extensibility without fracture. So there is large extensibility, that too without fracture. And also another aspect is that at low strain rates, at low strain rates, come on, the flow stress is very low. The flow stress, I mean the stress which is responsible for the dislocation movement or the plasticity, the flow stress is extremely low. So this gives us the advantage that this, if you have a complex shape of a superplastic material, so rather if you want to make a complex shape of a material, so you can very well make it under superplastic condition. So it is not only the material which is superplastic, there are superplastic conditions as well as like a temperature should be greater than 0.5 pm and low strain rates, everything that actually helps in creating a very complex shape like this. So the material or the alloy has to be taken into this superplastic condition to give it a complex shape. Now, if you go into the microstructure of a superplastic material or a condition which corresponds to the superplasticity, the grain size are very fine. It should possess a fine grain size. By fine grain size, it is assume it is less than 10 micrometers. And very interestingly, it should also have a presence of a second phase. And this second phase should inhibit the grain growth. It is similar to the process of popularly known as Zener pinning. Zener pinning is when you have a grain, say it's a collection of few grains, and normally with increase in temperature or say any type of stress being applied, there is a change in shape and size of these grains. But somehow, if you could manage to put some secondary phase at the grain boundaries so that any sort of change either in shape or size gets restricted. So that's the process of known as Zener pinning. That means if you as if you are pinning even these, like putting a pin on a paper so that it doesn't move. It's similar to that. So this property of or the condition of a material being superplastic is also similar to this. So they have a presence of a second phase which is inhibiting the grain growth at elevated temperatures. At elevated, or when the temperature is increased. Now, the most superplastic alloys are eutectic or eutectoid composition. Most superplastic alloys are either eutectic or eutectoid. So eutectoid means there is a transformation from solid to solid, whereas eutectic means liquid to solid transformation takes place. So by eutectic, it is meant that liquid is getting transformed into two solids, alpha and beta phases maybe, whereas eutectoid means solid phase is getting transformed into two more solid phases. So these two types of conditions are applicable to superalloys. Now, another aspect of the second phase that we discussed, which is hampering or which is inhibiting the grain growth, this second phase should be, or the strength of the second phase should be similar to that of the matrix phase. The strength, it is similar to that of the matrix phase, means that of the initial or the pristine phase, okay, or the base matrix. That should be comparable. And the reason why this condition should be there is that it is to avoid any sort of internal cavity formation. So it implies that there shouldn't be any internal cavity formation. Now, it may not be always be possible to have exactly the same strength. So to counter that, so if the second phase is not having the same strength, the another way to achieve the superplastic behavior is if suppose the second phase is harder. So in this condition also a superplastic nature of the alloy can be achieved, provided the matrix or the second phase, it should be finely dispersed, finely and homogeneously. It should be fine and homogeneously dispersed over the matrix. Let it a little more clearly. So the second phase should be, first of all, it should be fine and it should be homogeneously dispersed in the matrix. Now let's again concentrate on the grain. So these are the grains. Now this is again is subjected to some sort of tensile stress and the temperature is elevated. Now the process by which usually the grains change their shape or size is called grain boundary sliding. And since grain boundary sliding is the chief deformation mode, the grain boundaries should be high angle grain boundaries to promote sliding. Promote the slide. And secondly, so sliding, if the process of sliding is made easier, then the dislocation movement, which is actually the reason of plastic deformation, this will be little less. So let's say you have grains like this and the dislocation moves like this. So if the grain boundary are high angle grain boundary, by high angle grain boundary it is meant that, say, you have two adjacent grains kept in this fashion. Let's say 3 or 4 adjacent grains. The crystallographic patterns should be such that the dislocation, any dislocation passing through one grain to another, it should feed resistance because of this high angle crystallographic pattern. So it's easy, it becomes difficult for the dislocation to travel across one grain to another grain. So it prevents, or not exactly prevents, it gives more resistance to plastic deformation. because we don't want any sort of plastic deformation to be taking place in the case of a superplastic material. So that's why the grained high angle grain, or the grain boundary should be high angle grain boundaries. And it also, these high angle grain boundaries also, they prevent the formation of local stress concentration. So they prevent the formation of local stress concentration. So in the superplastic deformation, so let's recapitulate what is a superplastic deformation. How is it different from a normal deformation? So a dog bone shaped tensile sample, when subjected to tensile stress, and if we focus on this region, so in the normal case, there is a necking taking place, and followed by separation of the two separation into two pieces. This is necking, onset of plastic deformation, and this is fracture. Whereas in the case of a superplastic material, there will be no necking, but the material will be elongated. Okay, so that's the difference between the two. So in the first case, there is a movement of dislocation taking place from one grain to another, whereas due to high angle grain boundary, the dislocations are not able to move from one place to another, and there is a grain boundary sliding taking place, and there are high angle grain boundaries. And the grains are equiaxed. So after these sort of deformation or superplastic deformations is taking place, if you look into the microstructure, you will find the grains to be equiaxed. And the migration of the grain boundary is evident from these equiaxed grains. Now, this process is actually called a superplastic flow. That means a material without necking, if it elongates to that extent, it's about 1000% elongation. That means that it been 100%, so it becomes 10 times the original length. Now, there is when you are applying some sort of stress to a superplastic material, there has to be some activation energy. It cannot. There has to be some threshold energy before it starts to elongate in this fashion. Now, this is called we'll call it the activation energy for the superflow. Now, as this superflow is related to the sliding green boundary sliding, it can be said that this activation energy is equal to the activation energy for grain boundary diffusion. Or it, there are some alloys where this activation energy is equal to lattice self diffusion. So going to the mathematical aspect, now the superplastic flow rate represented by Salem dot, then it is usually equal to 10 to the power 8 sigma by E into B Burgess vector grain boundary size dgp divided by the length of the material, or rather this is the mean linear intercept measure of grain size. It's not the length, it has been called this L bar has been called the mean linear intercept measure of the grain size. But actually it means that you have, let's say you have a grain to grains, so just draw a mean between them. This is what it, so it determines the grain size. It's representative of the grain size. Okay. So there is a grain boundary diffusion taking place, and this is valid for grain boundary diffusion, and this is the Burgess vectors. Okay. Now, if the same thing is visualized for the case of lattice diffusion, so we can write the expression gets changed a little bit. So it's now it is equal to, so initially replaced into the power 8 by 2 into 10 to the power 9 multiplied by this one remains the same, squared it, replaced by the lattice diffusion constant V by L square. Now this squared, this exponent, this is called the stress dependence of power law. Stress dependence of power law, and usually so its value is 2. So now usually the strain rate sensitivity M is 1 by n, so that makes it as 0.5. So what we can say is that this deformation that is taking place, or the super flow or the superplastic deformation, so it is basically due to grain boundary sliding, which is accommodating the slip. By slip means that there is moment of dislocations. So this grain boundary sliding is accommodating the slip. So this is what is superplastic flow or super flow.